There you go.
I had problem 13, and you had to put the problem in sigma notation, and it was arithmetic, and I plugged it into an explicit formula to find the number of terms, and the part that went over here, and when I plugged it in, I got 34 terms, and negative 2 plus 3n, and then I put 34 on the top, and negative 2 plus 3n on the right, and n equals 1 on the bottom because you start from the first term.
So how do you know it's arithmetic?
Because you're adding.
Don't forget when it's arithmetic that you have to follow through with the formula. So you have to find the number of terms, you have to get an equation to go next to it. It's not like the ones that are neither, like the two we did yesterday in class. So there are a couple of steps that you need to do in order to write the arithmetic sequence. Any questions for Maggie on number 13? So how about number 12? What type of sequence is number 12? Yeah, number 12 was geometric. What were you multiplying by, Maddie? Yeah, you're multiplying by 1/10. So looking at number 12 was geometric. You're multiplying by 1/10. How do you find the number of terms when it's geometric? Because you still have to figure out how to get that number on top. Julia?
You'll have to put it in a log.
Yeah, you're going to have to use the log form. So number 12 started with 3, and then it went to 3/10, and then 3/100. Did it have another one? Yeah, 1,000, and then it went up to 1,000,000. So this is what number 10 looked like. So Maddie said it was geometric because you were multiplying by 1/10. And Julia said you're going to end up having to put it into log form to figure out the number of terms. So for a geometric sequence, we have the first term, the r, and then n minus 1. So Maddie, the first term is a 3. The r you said was 1/10. And then the last term on the other side that we set it equal to would be, what goes on the left side? That's all right. Right, 0.3001, or you could keep it as 3 over 1,000,000. Either way, it's the same exact number. This part right here is the equation that goes next to the sigma notation. So that's the equation. But you need to figure out the number on the top. So if we continue to solve this, we have to first get rid of the 3. So the 3 needs to kind of move away from that exponent because that's what we're trying to get by itself. Whatever has the variable is the part that we need to get by itself. So you can think of it as dividing by 3 because we do need to get rid of the 3. But when you have a fraction on the other side, dividing by 3 is the same thing as multiplying by 1/3. Now, without using your calculator, if you multiply 1/3 by 3 over 1,000,000 without using a calculator, because you're going to hear your teacher say that a lot next year in Trig Pre-Calc, how would you do that? Whether it's me or somebody else, I have even no clue what I'm teaching. Odette? The 3's cancel. So sometimes you guys want to revert to that calculator, and then the calculator gives you a weird number because the number is so small. And you don't need to always revert to the calculator. So the 3's cancel because I'm multiplying by 3 and dividing by 3. So I end up just having 1 over 1,000,000 equal to 1 over 10. So Julia said we need to put this in log form to solve for that exponent. So this is where, yes, you have to use the calculator. There's no way around the calculator once you get it into log form. So we have the log of 1/10, unless we lived 600 years ago, which we don't live 600 years ago. Even less than that, but they had all these log values memorized then. They had this really cool chart that they math people walked around with. I picture them literally walking around with their chart in their pocket, but that probably didn't happen. But maybe. So we have the log of 1 over 10, and we're taking that of 1 over 1 million. In your calculator, you need to use that log base function. So the log with the base of 1/10 of 1 over 1 million equals n minus 1. So make sure you remember where that is, because logs would be the first thing that we covered the second half of the school year, which will be on the final exam. Yes, we'll review for that next week, but that would be like one of the first things we covered. So, Julia, once you plug that in your calculator, you end up getting,
You get 6 equals n minus 1, and then when you add the 1, you get n 7.
you get 7. So that's how you end up getting that number on top of the sigma notation when you're writing the series in sigma notation form. And then again, the equation is the 3, 1/10, and then n minus 1. I'm going to make sure you know how to get that number on the top, because I see some of you that I've looked at just have the magical equation without any extra work to go along with it. Questions? So in your packet, if you can turn to, should be the last, second to last page. So you're going to actually turn to page 20. We're going to skip page 19. And we're going to talk about, still talking about series. We're going to talk about the infinite series. The last 2 days we talked about finite series. So the problems that we looked at had an end term. We knew where they ended. We could find the number of terms. We could find the sum because we knew how many terms were in the series. So just like sequences, sequences can be finite and they can be infinite. And we're going to look at series today that are in that infinite form. So again, it's page 20. So at the top, just as a reminder, an infinite series has no end term. Just like an infinite sequence has no end term. So when we had infinite sequences, we talked about graphing them and finding the limit, or looking at the numbers and finding the limit. So what did the values approach? Did it look like they were getting closer and closer and closer to a number? With infinite series, we're going to talk about something called finding the partial sum, because a series is a sum of the numbers in the sequence. So this would be finding the sum of the first n terms. Because it's infinite, I don't know how many terms there are. They're an infinite number. But I could find a partial sum, meaning how many would like the first 5 equal? Or maybe I wanted to take the first 10 and find out what they equal. Or maybe even just looking at the first 3. So a partial sum would be taking a couple of the numbers in the series and adding them together. Our goal is still to figure out what the sum of the series is. So is there a sum that they would all add to be? So a partial sum would be finding the sum of the first n terms. The sum of the infinite series would be literally the sum of all the terms. I'm going to put quotes around this. And we're going to see kind of like, does the series have a limit? And that's what we're going to kind of talk about today. I didn't put an S on my terms. There we go. So the first question gives us a series. And again, our goal is to find the sum of the series. So it says, does each series have a sum? If it does, find its value. So in order to do this, we're going to look at the partial sums. We're going to see if we can find some partial sums. We're also going to look at it graphically to find out if the series has a limit. So that's our goal. Does the series have a limit? Are they approaching a value? So a series, similar to a sequence, we have 4 and then 0.8, 0.16, 0.032, 0.0064, and then it continues on and on and on. Anybody kind of look and decide, is this arithmetic or geometric? So what are you doing to get from 4 to 0.8 to 0.16? You might need to use your calculator. To 0.032. Connor? So if you say multiply, that means we have geometric, and he said multiply by 0.2. So we know it's geometric, we know you're multiplying by a number less than 1, you're multiplying by a smaller number of 0.2. So my numbers are getting smaller as well. So we're going to see if the series has a sum by finding the partial sums, and I'm going to show you how to do that. The first couple of problems of your homework, 3 to 6, ask you to find and graph the first 5 partial sums. So we're going to do that same exact thing. So we're going to find 5 partial sums. I already have the first 5 numbers of the series. So to find a partial sum, we're going to use an S instead of the sequence notation. Oops, sorry. So we're going to find the sum of the first term, which would just be 4, because one term is just going to add to be 4. The second partial sum means add the first 2 terms together. So now we're talking about adding numbers together that are in the series, because that's what a sum is. So Julia, 4 plus 0.8 would be 4.8. So now I have 2 partial sums. Well, the goal is to get 5. So I'm going to continue this process. S3 means the sum of the first 3 terms. Well, I already have the sum of the first 2 before it. So if I just add that extra number, taking the 4.8 plus the 0.16, and Julia, that gives us 4.96. So now that's the sum of the first 3 terms. So continuing this process, taking the previous sum, because that's 3 numbers added together, and adding the next term, and then doing that one more time, taking the previous sum, adding the next term. So Emma, the sum of 4 terms would be, and then taking that number and 0.0064. And Emma, that becomes so those will be the first 5 partial sums. So similar to finding terms in a sequence, except a sequence you just list the terms and then we would graph them. However, in a series means you're adding terms together, so we're adding the terms. So if you just looked at these partial sums, what does it look like the number that they're getting closer and closer to? Does it appear that they're approaching the same number? Odette? Yeah, it looks like they're approaching the value of 5. So we would say the sum of the series is 5. Now you'll be asked to graph and find the sum. So if you have any extra space on the side, I'm just going to make a little graph. This is just like graphing a sequence. So 1, 2, My first partial sum was 4. So I'm putting a point at the first sum, which is 4. My second sum was 4.8. My third sum was 4.96. And then it got just a little bit higher each time. You don't connect them because they're just sums. So it's not an equation that's continuous from one point to the next. So graphing, I can see that these are curving towards the number 5. They're leveling off of the number 5, kind of just going horizontally. That also means that there is a sum at the value of 5. Questions? So, does each series have a sum? Yes, this one does, and that sum is 5, because those numbers are getting closer to 5. So see if you can do the same thing for the next example. We have 1, -1, 2, -2, probably then 3, -3. You want to find those first 5 partial sums. So the second partial sum would be adding the first 2 terms together. Now we're adding, we're finding the sum. And you get 0. So then you're taking 0 and adding the third term, which is 2. And then I take that sum and add the fourth term, which is -2. And I'm back down at 0. And then I would have a 3 and a -3 as my next numbers. So again, I'm taking 0, adding the fifth term, and I get 3. So I could continue this, but we gotta find 5. We could find 10, we could find 20. If we make a little graph of this, your x-axis will always be the same, 1, 2, 3, 4, 5, because you're gonna plot 5 points. The y-axis might change depending on how big those numbers are. Now they only go up to 3, so my numbers aren't very big. But sometimes those numbers can get larger depending on what the numbers are that are in our series. So we're graphing the first sum at 1, and then the second sum is 0. My third sum is 2, and then we're back down to 0. And then the fifth sum is 5, and I bet the sixth sum would be back down to 0. So Maggie, would you say that this series has a sum? Does it look like those numbers are getting closer to the same value? No. This series does not have a sum. Looking at the numbers are going to go back to 0 and then up to the next number of 4. Back to 0, up to a further number away as 5. The graph, if these points continue to spread apart, they're not getting closer together. That's when there is no sum. So for there to be a sum, for there to be a limit, the points need to get closer and closer and closer to the same value. They can't spread apart and get further away. Questions? So of course, that's one way to find the sum, by graphing and finding partial sums. But there has to be another way, because somebody created a formula that makes it way easier to solve instead of finding all of the sums and graphing it and trying to analyze the data, because that's what math people do. So there's a little box that says the sum of an infinite geometric series, and that part there is really important. It must be geometric. For a series to have a sum. So if it's not geometric, then it doesn't have a sum. Done. Must be geometric for the series to have a sum. There's 2 conditions, so it must be geometric. And the other part is looking at the R value. That's that ratio. What are you multiplying by? If the absolute value of R is less than 1, then the sum is equal to the first term divided by 1 minus r. So the absolute value of r is that ratio. So for the first problem we did, the ratio was 0.2, which is less than 1, which is why there was a sum. If the absolute value of r is bigger than 1, then there is, again, no sum. So there's only a specific case for there to be a sum for an infinite sequence or series. It must be geometric. If it's arithmetic, there is no sum. If the r value is bigger than 1, there is no sum. And we say absolute value because it doesn't matter if it's positive or negative. So if it's a negative 0.2, that's okay. If it's a positive 0.2, that's okay. That's why we're saying the absolute value. Questions? So on the next page, there are 4 or 5 examples. We're just going to look at those examples and try and decide, is it geometric? What's the r value? Because that's the condition that must be met. Those two things, geometric and r must be less than 1. If so, then we can calculate the sum. If not, then you just say there is no sum because the graph isn't going to have a limit. So the directions, does each geometric series have a sum? If so, what is it? So we have 4 4/5, 4 over 25, 4 over 125. So we need to figure out the r value. What are you doing to get from one term to the next? Odette. Multiplying by 1/5. So Odette, is the absolute value of that r less than 1? Yes. The absolute value of 1/5 is 1/5. 1/5 is less than 1. So it has met the condition. Once the condition is met, then you can find the sum by taking the first term and dividing it by 1 minus r. Again, some math guy in the 1400s found this pattern to get the sum of sequences, the sum of series. So taking the first term, which is 4, and then you're dividing that by 1 minus a fifth, which is really 4 divided by 4/5. Abby, what is 4 divided by 4/5? It is 5. This happens to be the same series that we just did on the previous page with the partial sums, except they were as decimals instead of being as fractions. But the same one, just listed as fraction values instead of decimals. So there is a sum, that sum is 5. So you can kind of prove algebraically, we have a formula. Graphically, you're finding those partial sums. You can see that they are the same value. So looking at number 2, we have 3, -2, 4/3, -8/3. And again, we need to figure out what the r value is. What are you doing to get from 3 to -2? From -2 to 4/3. Connor, what do you think?
Multiplying by -2/3.
So he said multiplying by -2/3. Connor, how'd you figure that out?
Well, -2 would really be -2 over 1. If you multiply that by 2/3, then you get 4/3.
Yeah, so if you have -2 over 1 and multiply that by -2/3, that's how you get 4/3. Sometimes if you just look at the two fraction values and compare them. When you have fractions, sometimes it's easier just to compare the fractions together. What do you do to get to 4 to -8? Well, I have to multiply the top by -2. To get from 3 to 9, I have to multiply the bottom by 3. So think of it more in terms of what are you doing to the top, what are you doing to the bottom, and then just make sure that applies to the rest of your problem. Bless you. So, Connor, is the absolute value of that r less than 1? Yes. The absolute value of 2/3, -2/3, is 2/3, which is less than 1. So our condition is met. Make sure you're meeting that condition, because then you can find the sum. So 3, and then 1 minus -2/3. Connor, what happens when you have 1 minus negative 2/3? What's that become?
Plus 2/3.
Yeah, so this is 1 plus 2/3. Gonna make you use a little bit of mental math here. 1 is really 3 over 3, so Connor, 3 over 3 plus 2 over 3 is 5 over 3. So we're taking 3 divided by 5/3. You know what this sum is? What's 3 divided by 5/3? Julian? 1.8. Can you give it to me as a fraction? 9/5. 9 over 5. Remember, when you're dividing by a fraction, you're multiplying by the reciprocal. So I'm dividing by 5/3. Really, I'm multiplying by the reciprocal. That was chapter 8. So multiplying by 3 over 5. So looking at the next one, we've got the sigma notation. It's okay for it to be sigma notation. Notice in the bottom, there's still that 1, but the top we have that infinity sign. That makes it go on forever. That makes it an infinite sequence or an infinite series. Just a reminder about sigma notation. You have that first term, and then we have the r, and then the n minus 1. So that would be the form of sigma notation, just so you're kind of looking to see where the piece is falling. So what would the r be in this sigma notation? What's r? We need to find r. Julia?
It's the 0.5.
Yeah, the r is the 0.4. The piece that's connected with the exponent is the r value. So r is 0.4. Julia, is the absolute value of that r less than 1?
Yeah.
Yes. So now we need to figure out the first term, because the formula says take the first term divided by 1 minus r. So again, this is what a geometric series looks like, or a geometric sequence looks like. We have the first term, r in parentheses, attached to n minus 1. What number is in front of the parentheses? Odette?
1.
A 1. So there's really a 1 sitting here in front of that parentheses to represent the first term. Another way you could figure that out is by plugging a 1 in. So I could take 0.4 to the 1 minus 1 if I want to figure out the first term. I get 0.4 to the 0 power, which again is 1. So you can find the first term if you're not sure what it is by plugging a 1 into your equation. So we have a 1 divided by 1 minus 0.4. So my first term is 1. We're dividing that by 1 minus r, or 0.6. So what is 1 divided by 0.6, Kushal? 5 over 3. So see if you can do number 6. And then do you guys have a 7 on there? Yes, okay. So why don't you try number 6? I'm going to pass out some graph paper. So you need to figure out what r is. And then find the sum. And then why don't you take a peek at number 7? Mackenzie Mallory, what's the R value in number 6? And is that R value less than 1? Yes. So if we're finding the sum, the first term is 3, and then 1 minus a fourth is really taking 3 over 3/4. So Mackenzie, the sum would be 4. And then the last problem, which I thought I had one on here. I don't know where mine is. Can Tatum, can you give me the last problem, the numbers there? You said plus negative 18, right? And then plus 54. Thank you. What's the R value? What are you doing to get from one number to the next, Eric?
-3.
Yeah, multiplying by -3. Is the absolute value of that R less than 1?
No.
No. The absolute value of -3 is +3. +3 is not less than 1. Those are the ones you're going to like. There is no sum. If there was a problem that was arithmetic, there would be no sum as well. So arithmetic has no sum. If the R is bigger than 1, there is no sum. Absolute value of it to make it a positive number. Questions? So the homework is on the board. Again, it's in the book. This is the last book assignment. Tomorrow we're going to do a handful of notes as like kind of just a review of the Infinite series. And that was like the last packet notes that we'll have. Gabby and Ellie, would you be interested in doing 3 or 5 tomorrow? Okay, so yes for 3. You said no. Graham, you want to try number 5 for tomorrow? Sure?